We scheduled Elango on Leap Day. As most of you know, this doesn't happen that often. Most usually every 4 years, but what you're about to hear about today is something that has never happened before, and that's getting to an oxygen electrolyzer on Mars. Mars is the closest the two planets get is about 33 million miles apart. And the furthest they are apart is about 240 million miles. So you can imagine the logistics of just planning that trip. But you're going to find out that what these guys pull off is just as difficult. I've known Elango for a long time. We went to school, graduate school at the same time, back when dinosaurs were roaming the earth. And he joined a little company called Ceramatech that no longer exists. And we worked together at the same company for about 3 decades. He did his bachelor's degree in India and then did a master's degree at Caltech and came to Utah and did his PhD for a fellow named Mark Plichta, who's doing massive transformations. And he lost his PhD advisor right towards the end of what he was doing. His professor transferred, so you imagine how tough that was. Figured that out, and then while they were right in the middle of the projects he's going to talk to you about, the company he was working for decided they were going to leave Salt Lake. So same thing, deja vu again. And his company left, and he and Joe Hartvickson, a chemical engineer, and Lyman Frost, who is kind of a business guy, they decided to form their own company. And they've pulled this off without any borrowing of money. And it's quite an impressive company. It's called OxEon Energy. They're located in North Salt Lake, and Dr. Elangovan is the chief scientific officer. And just a great story you're going to hear today, and very grateful that he would take his time to come and tell us about this journey to Mars. So we'll turn the time over to Dr. Elangovan. Let's give him a warm round of applause.
Okay, thanks, Raymond. Thanks for invitation. I've given talks a few times here on campus, and some in metallurgy department, some here before the two departments merged. But I have not given a talk on this particular project, so it's my pleasure to introduce this topic. And this is one of those things that happens once in a lifetime. After the project ended, Joe, who is my business partner now, and I talked, if we retire, it'll still be something we can be proud of. That's such an accomplishment. Of course, at the peak, we had close to 30 people working on that at Ceramatech, and not counting people at JPL and MIT. So it was a big project. So I'll go through what we did. It's kind of the motivation for that and what we have done and where we are going. So if I go way back, most of you probably don't remember what it was like in 1969. That's when Apollo 11 landed on the moon, July 21. What is interesting is that's a couple of days after my birthday. I turned 13. So most people, if you lived in those times, would remember what he did when they landed. He would remember, and many of you may not even know the excitement all around the world. It's not just in the US. So Neil Armstrong stepped on it and made his famous utterance, "One small step for mankind." So that's why I call the whole thing one small step. But things got drifted, but we don't need to go there. So what I was doing, I was middle school in this house. Nobody lives here. It has seen its better days. All my siblings moved out and my parents passed away. This is where I was. I was listening to the broadcast of the landing on the radio. It's not even a transistor radio, it's a vacuum tube radio. That's what we had. So I was curiously listening to that, and then, there was some, obviously the original broadcast, and in some of the channels from Sri Lanka, they had Tamil broadcast of the, simultaneously they'll translate, so I was switching back and forth. I was in 8th grade at that time. And then, a couple of years later, Apollo 13 disaster happened. I wasn't following it that closely because I was busy. But after the astronauts came back, there were a lot of news articles. In fact, it was an accomplishment for NASA to bring them back. Most people thought that's the end of the mission, and the astronauts came back. The local newspaper, maybe Sevaran might know, there's a newspaper called Dinatandi. A year after Apollo 13, they had a serialized 4 or 5 week worth of what happened to Apollo 13, and then all the background of the NASA mission to the moon. So that was fascinating. That serialized article was the first time I even heard the term fuel cell. And some of you may know what happened was the oxygen tank ruptured. So there's a connection to oxygen, and it was feeding the fuel cell. So since the oxygen tank ruptured, there was no power, it's barely any power. So they were freezing, and NASA was able to bring them back. So to me, not that, I can always look back and say, oh, I wanted to do something like that, but it just made an imprint. NASA would be a cool place to work, but I had no idea. I had never met anyone who had gone to the US. Zero. It's not like I know what to do to get here or anything, but I had somewhat of a dream. Wouldn't that be cool to go to the US, get a graduate degree? But being in 8th standard, we call it standard, 8th grade, I only known a few people who had gone to college by the time. None of my classmates from high school went past a year or two of college, and they all got a job. So that's the start of it. I'm saying that because sometimes, you have kind of an inkling, but you don't know what to do, or if it's even possible. So now that's the background. Fast forward to now, just if you imagine the coldest, driest, dirtiest place on Earth, and it's the atmosphere is as thin as you are 20 miles above sea level. But that's not enough. There's no oxygen in the air. You only have tiny bit of not even nitrogen. There is ppm level nitrogen, but it's all filled with carbon dioxide. But that's the ambition. Should we go there? What does it take to go there? What do we need if we ever get there? So that's kind of a dream. As Raymond said, that's the closest planet. So if we want to venture out to another planet, that's the relatively easy opportunity in terms of distance. And not only that, it takes 7 months to get there. Even when it is the closest, and the rocket travels, I think something like 40,000 miles an hour kind of speed, it still takes 7 months because Mars is not stationary. You kind of you have to chase it down to reach there. So it takes 7 months. And I have another chart that'll give. But you have to stay there for at least 18 months. That'll become clear why. And then the sunlight is dimmer because of the distance, and the days are not 24 hours, it's 24 hours and some minutes, 37 minutes. And the gravity is not as strong. So there is water, but you have to dig, I don't know how much, or you have to go to the polar regions. There's no water. And communication is the biggest, if you've seen the movie Martian, he'll send one letter at a time, because in that story, it took 24 minutes to get the message from Mars to the Earth, and then 24 more minutes. So depending on the distance, you just cannot talk continuously. If your cell phone signal is bad, we get really upset. Can you not hear me? So, but if you remember the old commercials, that was the main focus of a series of commercials. Can you hear me? So that's, if you think pandemic was, God, you're stuck, So if you get to Mars, you cannot leave for 18 months. It's not like the contrast to Apollo 13 is, on the third day they had the problem, so NASA figured out to have them swing around the moon and come back home in 3 more days. So if once you leave, you're committed for 2 years. You just cannot come back. Even if you land, you cannot say, oh, I don't like this place, and I pack up and go back. It's just incredible thing. So the commitment has to be there. That's why I cannot imagine how brave people who commit to go to Mars. There are people who are training. So Mars being the nearest planet, there are a lot of stories. People talk about the green Martian, and there are no people, at least no life we have identified yet. But that's always curiosity. Mars, in a lot of ways, is similar to Earth. So was there any life on Mars? There are some differences, but the other thing is Mars is a greenhouse extreme. It's all 96% CO2. Was it ever habitable? What happened and why is like that? So all kinds of investigation and the curiosity that leads to those investigations could teach us, is there anything we have to do before we become another Mars? And people talk about we can build a colony. If we fix Earth, that's so much easier than reversing Mars, but that's a separate topic. So we can learn a lot by going there. Why do you have to go there? Can we send robotic missions? We have done that. One of the interesting things about Apollo mission is initially they were without astronauts, robotic missions. The very first astronauts, when they got on that, apparently, the first comment they made is, what is the smell? They smell something. It's probably molten glass kind of smell on the soil, but every mission, they thought, we have never smelled anything like that. So there is, and also when they explored, later on in few Apollo missions later, they had an electric car they were driving around. So they did sort of unplanned activity because they saw a mountain kind of arrangement, so they drove. Robotic missions will only do what we already know, what NASA tells it to do. So there's a lot of things. So when eventually someday, maybe in our lifetime, I don't know, when people go to Mars, you may learn a lot more when people are actually get there. And there are a lot of benefits also. There's a lot of international cooperation. So people get excited about space missions more than any other scientific investigation. So there are opportunities for that. I don't need to smell that, not for this audience. I've talked to people. They'll always question, why are you wasting so much money on space missions when we can spend that money to eradicate whatever, fill in the blank. But so much technology comes out of that because, for example, we did the stack for the Mars mission. There are some requirements we wouldn't have cared about if it is strictly for Earth applications. So that gave us, I'll mention a few things of that. So there's a lot of technology that comes out of space missions. So when we go to Mars, when astronauts go to Mars, I said that carbon dioxide is what is in the atmosphere, 96% carbon dioxide, which means the first thing they need is oxygen. Oxygen, typically people think oxygen is for the astronauts to breathe. That's a very small amount of oxygen they need. The largest quantity of oxygen astronauts need is for the return vehicle. So that's the biggest consumer oxygen. Then obviously they would need water. There is water, but we have to dig deep or land near the poles or find a way to transport from the poles to where they land. So those are somewhat uncertain. I'm sure NASA has plans, but it's not public yet because they are figuring it out. And then radiation is the biggest problem. There's no magnetism on Mars. That means radiation hits hard. So if they go, they have to build a habitat that includes radiation shielding. And then waste management. So we take a lot of things for granted. And then the biggest thing NASA talks about is, can we make what we need on Mars? That's the focus of our project is. Again, I'll talk about that. This is kind of the Mars mission. I told you it takes a long time, so we have to leave, but Mars may be somewhere here, but by the time we get there, it took just a little shy of 300 million miles of travel from launch to landing. I always amaze myself. They landed within probably 20 yards of where they predicted. I cannot even park in the parking spot without getting, I have to get back and straighten it. So that's way beyond my comprehension, how would they calculate. And then once they land, Earth keeps moving, and then, like Raymond said, it becomes the farthest. You just cannot leave. Even if you have technology, rocket technology leave, the less time you spend in the radiation space, the safer it is for astronauts. That's the biggest concern. So you have to wait for Mars and Earth to be on the same side, and then leave to come back home. So once you leave, you're committed. This Mars and Earth coming on the same side, they call it launch window, occurs every 26 months. So 7 months of travel, you have to be there 18 months before you leave, so that close to 26 months. So it's a huge commitment. Yeah, the closest is 35 million, and the farthest is 240. And oxygen, like I said, it's not just oxygen is needed for breathing, but the biggest, anything you burn on Earth, you don't even think about it, because oxygen is available in the air. You just put the fuel and run it. On Mars, there's no fuel, there's no oxygen. So you have to worry about that. The biggest consumption, the heaviest thing we need there is the oxygen. You can take oxygen from here, but typically it'll take about 3 to 4 launch, at least 3 separate launches, because how much fuel you need to blast off a rocket depends on how much you're carrying. The more you carry, the more fuel you need. So there is a limit of how much oxygen you can transport on a single mission. So it'll take at least 3. And then the risk, everyone has to be successful for astronauts to leave on Earth. The plan right now is an oxygen-producing machine will land there, run for a year, at least Earth year, and then fill up the rocket that was already launched 2 years prior to that. When the NASA knows the rocket is filled with the fuel and oxygen, then the astronauts will leave, because there's no way to predict something won't fail. So that's more or less a 6-year planning. When it'll happen, we don't know. They're talking about mid-2030s. So hopefully we'll get to see it, Raymond. This is what we made, just a schematic. Many of you have taken material science class. You may have. The first time after my 8th grade, the next time I heard about fuel cell was Professor Wirkar's class. He talked about fuel cell. Oh, there's fuel cell I heard about years ago. This is the reverse of fuel cell. So this is the zirconia ceramic electrolyte, and then that at high temperature, around 800 C, is an oxygen ion conductor. So when you apply a potential across, and when you have, in this case, carbon dioxide, it could be steam, it splits the molecule and moves the oxygen ion through it, and the electrons are released, and then the pure oxygen comes out. On Earth, we don't care about making oxygen. Essentially, there are some applications where oxygen or oxygen-enriched air would be useful. But here on Mars, that's the commodity that's not available. So making oxygen is the biggest one. This is called solid oxide electrolysis. NASA called it SOXY, but here we call it solid oxide electrolysis cell, SOEC. Here's the device. I brought the stack. After the end, you can come and take a look at it. This is not a mock-up. It's one of those things when people are recruited to go to Mars or Moon, they'll have dozens of people, they'll pick a few. We made more than 50. This was an unlucky one that didn't go to Mars. His companion went. It's still on Mars. So this is the unit. The carbon dioxide goes through one port, and then it gets electrolyzed. It has 10 layers, so each layer will act independent cell to make oxygen, and the collected oxygen will come out of the port. I'll talk about some of the design aspects and materials aspect. So that's the basic unit. So we made this, Raymond mentioned the company Ceramatec. This project was given to Ceramatec. So we made all the units at Ceramatec and delivered to NASA. A month after we delivered is when Ceramatec announced we are closing down the company at the end of the year. So 3 months later, the company was gone. Interestingly, a lot of NASA people called us saying, hey, it hasn't landed yet. It left. Well, it hasn't. Yeah, anyway, we delivered, but they were waiting for the launch. If this is wildly successful, what would you do for the next mission that leads to going astronauts? And we said, yeah, you have all the process documentation. They said, we cannot just take a binder with instructions and give it to somebody. So that gave us some confidence to start a company. And that was a good decision. Anyway, so this is a schematic. I brought a stack here. So it's still on the rover. I'll talk about what is accomplished. It traveled 293 million miles before it landed. I always joke, I should ask for frequent flyer miles for our unit. I didn't. So overall process, I'll just briefly say that Mars is a dusty place. It'll have storms and even dust devils. There are pictures and videos of that. So the CO2 has to be filtered. That was a worry. What happens if the filter is ineffective or the pressure drop is high? But there's a British team that built the filter. It worked flawlessly. No pressure change. It didn't contaminate the unit. And there's a pump that compresses called scroll pump. You can find out more about it. Anyway, it worked very well, but we don't know if that's adequate for the manned mission, whether it will run for more than one Earth year. This is the pump that compressed it, schematic of the pump. Now comes the hard part. We knew it has to make oxygen. There are a lot of requirements NASA didn't tell us. They said it has to make oxygen on Mars using carbon dioxide. They also said it has to make, the production rate should be 6 grams an hour. So we calculated how many cells, what kind of performance it needs to have, and we had a design and plan for that. They said it has to be more than 98% purity. We had never made a stack with seal good enough that could make 98% purity. On Earth, we don't make oxygen, but we make hydrogen from steam. And if there's some leak of hydrogen, it'll burn inside the cavity. If there's some oxygen leak, it'll burn, make water. It's no big deal. So nobody wants 98% purity, even though there are some plants, people could use that. And then the other thing is it has to operate 10 times, which we know, even though eventual for manned mission will run for a year, ideally you turn it on, make oxygen for a year, make enough oxygen, 32 metric tons, you're done. Here, this is sitting inside the rover. That means we need to rely on the battery to power this. The battery is not available all the time because they had 6 other instruments on board, so we had to share. So they'll give us a time, there's 3 days available. So MIT was in charge of the operations. They'll write the code, whatever we need to do, and it'll be uploaded, and then it'll run. So 10 times, yeah, that's not a big deal. We expected there'll be multiple operations. I mentioned NASA's plan is to make what we need where we go rather than carrying it, because imagine if going to Mars is that hard if you're going to another planet, maybe 100 years from now. We cannot carry everything they need, so it's always a plan. They call it In-situ Resource Utilization, which essentially means make what you need where you go. And they call it living off the land. It's almost like what pioneers did. They didn't bring everything they need for a year. They figured it out after they got here, but things are different when you go to Mars. The risk is the biggest worry is if we know what you need can be made, and in fact, it's already made before they leave, there's an assurance they can live there safely and leave the planet. So that's the plan. And the cost saving is always in the back of people's mind. Instead of 3 launches, we have 1 launch with a machine that makes oxygen. I co-authored a paper that talks about living off the land and a lot of other technologies. I wrote the section on the oxygen production. So NASA said they want to send something to Mars to make, they had an open solicitation, and we made a bid with Jet Propulsion Lab and MIT. The proposal was selected 2013. Initially, yeah, the launch is 2020. Oh, we have plenty of time. They said, no, you have to deliver in 2017. So we have to do a lot of tests with the stack, and then when it's assembled into a unit, that needs to go through qualification outside the rover and installed it in the rover, and it's like a series of tests. So we had less than 4 years to do something for the very first time. We didn't know what needs to be done, but we figured it out. MOXIE is 0.5% of what is needed when we send astronauts, so we have to scale it up 200 times. So that part is not that difficult. Just we have to make more cells, but there are flight qualification type of work we need to do. So here's the design. It may be hard to see. So we have the frame, seal frame, interconnect, cells, and so on. So overall, it's a multiple layer. Cell is the main one, zirconia electrolyte with CO2 electrode and oxygen electrode, and then we put the interconnect. This may be, if you're not familiar with that, maybe a little bit hard to follow, but essentially, this is what we have been doing. Steam is the feed gas. On Mars, it'll be CO2. Product is hydrogen or hydrogen carbon monoxide. If something leaks out, leaks in, it's not a big deal. But initially they said 98 in the solicitation, but after we got the award, that's not good enough as a propellant, so you have to get 99.6. So, oh yeah, sure. Main thing is the seal. Raymond probably recognizes that. If you go to any fuel cell conference, they say challenges to make a fuel cell, they put seal as a number 1, and then oxygen electrode as a number 2. So we were supposed to solve the seal problem in the 4 years. We have worked close to 25 years prior to that. We never had a good seal. It's always leak. We didn't have to worry about perfect seal because it's good enough. And then weight is the constraint they gave us. It has to be less than 1 kilogram. Volume is also, you have to, this is all the space you have in the rover. This was a scary one. Usually, it's a layers of ceramic that's 250 micron, and then the interconnect. We usually start it before we leave, 6:30, 7. It'll be hot in the morning. So usually 8-hour heat up time. They said you only have 90 minutes to heat up, because the longer it takes, the more energy will drain from the batteries. If you need energy, there's 1 kilowatt hour is the maximum available to you. So you have to heat it up really fast, run it for 1.5 hours of heat up, 2-hour operation, then cool down. And nothing will happen because it'll pretty much drain the battery. So for another day, they'll just charge it. So that was a biggest one. So it's practically 500 C an hour heating rate on Mars. It's not like we can go swap the stack. And then, anyway, so that's a big challenge. So the heating rate worried us, purity worried us. So what we changed is we used to use ferritic stainless steel because it's inexpensive. It didn't seal very well, but that's fine. So we changed the material. There's an Austrian company that came up with this composition, which is perfectly CT matched from room temperature to 1000 C with zirconia. So we have no other choice to start with the material we have never worked with, and then we worked with another German company to find a seal. They had it. So interestingly, that worked so well. You know, I wasn't expecting it'll work well. And then there are other changes. We didn't change the oxygen side electrode, but some minor changes to the CO2 side electrode. So there's some changes. One of the first thing NASA people said is, this is not an investigation of discovery. You cannot change anything, but you have to make it work. You know, it's like concerned about that. So we sneakily made some changes. You know, because otherwise it won't work. And I may have another slide. They also said, whether you are ready or not, is leaving July or August of 2020. So if you don't have anything, that's it. It's not like, it sort of works, we'll send it. So it has to work, meet all the requirements for them to say, we'll load it. The other thing they worried is, it goes to 800 C. You want to put something that goes to 800 C inside the rover. It's a $2 billion mission. So do no harm is the first thing. That was not, you know, that was not a problem. You know, as long as you put insulation and control it properly. But still, they never had anything that hard inside the rover. We did the very first test, panicked everybody at NASA and JPL. We operated it. Yeah, that's good performance. This is kind of a measure of the resistance. You know, 1 is very good number. Since we have to do 10 to 20 operations, we cooled it down, heated it back up. It doubled the resistance. That means oxygen production is 50% of where we started. We kept doing, and by the 15th cycle, it was making 12% of the oxygen at the start. They all said, you need help. Not that they know what to do, so they wanted to institute a tiger team to help us. So we said, no, thank you. So we had a really good program manager. She could handle, you don't need help, and convince them they don't need to help us. Essentially, they want to have lots of meetings as to what went wrong. I said, this is the first test. We're learning where to fix it. So this one, essentially what happened is, this is the nickel-based electrode. We didn't want to change it, and a lot of people suggest if you use ceramic-based electrode, it won't oxidize. Yeah, sure, but the performance will be 1/10. You know, we have seen the literature of what people report. So with dry CO2, the nickel oxidizes, and from inlet to outlet, each cycle, it'll progressively oxidize, and by the time we did 15 cycles, there's not enough nickel left. And once it oxidizes, it'll also flake off from the zirconia. So that was the problem. Then took months for Joe to convince this can be solved if you recycle the produced CO back into the, oh, that complicates the system. We cannot do that. You know, they want anything new we add, they were concerned it increased the risk, so we had to convince. So that's one. So which essentially means thermodynamically you need to have about 0.55% CO at the inlet. So what Joe proposed is, within a minute of operation, recycle the exhaust back to produce at least 0.55. We had 2% CO recycle, so that solved the problem. We tested it in the laboratory also, adding 2% CO, that worked well. The other problem is carbon deposition. So if you take, this is the open circuit voltage, so at no dry CO2 is kind of, you cannot define it, so let's say 10% carbon monoxide produced, that's a voltage. So you go up in voltage, it produces more and more CO, which also means it produces more oxygen. But there's another line that's coming from, this is for CO to carbon potential. If it crosses, you're dropping carbon out. That means you have to stay before it crosses. But since the inlet outlet is this area, so we have to get an average somewhere here, even maybe here, that means you can only go to about 40% conversion. You have to stay below. And then this stack, we are not allowed to put leads on every cell. So you only would know the total cell potential. You have to make an assumption it's evenly distributed and then give a cutoff. We set 0.1 volt as the limit and hoping the average and the individual cells are really close to each other. It worked, but that was a big. Then people said, we spend so much energy compressing the CO2, putting it there, you're only converting 40% of it. I said, that's the limit. We have to come up with that. So that one, we didn't change anything. So we had the recycle to get about 0.55, 2% inlet CO. Conversion is no more than 40%. That's the window we operated. So this type of analysis Joe did, people have never done it. People are talking about CO2 electrolysis on Mars for decades because it's the concept is fairly straightforward. CO2 is available, you can make oxygen, but people never comprehended the upper and lower limit. Joe was the first one. Now we know, again, it's a bulk inlet CO and outlet CO. But could we get the same, for example, this area, this is the design. Again, Joe came up with that. If you have more CO flowing in one area, less will get the carbon limit sooner and where it has less. So this took CFD analysis, current path analysis. Current has to be uniformly distributed, which means the current over here and then the distance between the pins that contact. It's a very, very complex, and the time is limited. It's not like you can take years and years to perfect this. We had to quickly calculate that, come up with the flow distribution and the current density distribution. Everything has to be as uniform as you can get. Otherwise, in the low flow area, we'll deposit carbon, especially when we are running blind. We don't know what local voltage is. And then the structural analysis. I may have another slide, but I'll tell the structural analysis. This is all, they're adding more and more flight qualification. You have to do this, you have to do this, and so on. Not just coming up with the right material set and the production rate and carbon deposition, which nobody recognized before. They said, since this is going on a launch, it not only has to meet the shock and vibration, because if you watch the window, you could practically feel the shock waves coming. It experienced that shock. So to avoid the packaged unit from rattling around, we have to put it under very high compression, 2 kilonewton compression. I said, we never compress our stack. We gingerly tighten some screws so it stays together. So that means we had to do structural analysis to make sure the load they're putting is evenly distributed. And I mentioned 250 micron zirconia electrolyte at 800 C. So it's not very strong. So not only the cells have to be flat, and the interconnect with all the gas channel pins need to be nearly flat. It wasn't perfectly flat, but the team at Planze in Austria, they worked with us, and they made it really high quality, flat one. Not 2 kilonewton minimum, but they always want some extra in case. So I think they gave us 4 kilonewton for the packaging. And they always say, this is the requirement, you have to show it works 3x. So we did 10 kilonewton is the compressive load. We tested it. It's all cold compression, not at temperature. And then tested it, and oxygen purity did not change, and stack worked well. Then 25 kilonewton to see if it can survive. It survived. We were all amazed we can put 25 kilo in tank. And then it took more than 60. I think this is about 6,000 psi cold load. And people always joked, this is one African elephant, there's 2 African elephants standing on it. And I always joke, Americans will use any unit except the metric system. So this is our unit there. So, and then after, we didn't do the, 62 is when we know it cracked, cells cracked. 25 did fine, and 10 was, so we tested it. We were still getting the better than 99% purity, nothing cracked. And not just the ceramic layer, it has the glass, molten glass on the edges, that survived also. And the flatness was adequate to not do point load. We sent stacks to JPL, and they did, shock and vibration test, and it survived. And they'll test it and send it back, and then we'll put it in our furnace and test it. The main concern is current is proportional to the oxygen production rate. Do we hit the current, and is the oxygen purity remains the same? It did. And the next test they said is the shock test. They'll mount the stack to a beam and shoot this 4-inch diameter aluminum projectile to shock the beam. And then they did that and shipped it back. Sometimes they would hand carry it. The TSA at the airport knew the NASA people. The first couple of times they had to show a letter. They're carrying something for NASA. Then they all became familiar with the people, so they didn't bother. So they'll carry it back, and we tested it. And again, oxygen purity was good and the current was good. Next comes okay, this is done. They said Mars could get to minus 40 C at times. So we have to test it at cool it down to minus 40. And I said, yes, but we need some margin, go down to minus 65. I scoured the literature. We don't know what this chromium alloy would do at minus 65, what zirconia would do. I should have called Raymond if he had any reference. There's nothing. There's absolute nothing. This is one of those things we all said, I hope it works. They may do it minus 65 and take it out. It's all crumbled pile of powder. There's no recourse. Oh, it's not like we had a plan. Oh, if that happened, we have backup plan. Nothing. But incredibly, it survived. They took a stack, went to minus 40 to room temperature 40 times, and then 3 to minus 55, and then 1 time to minus 65. And here's the stack tested. We stuck it in, took it to 800 C, same current, same oxygen purity. This is one of those things, you need luck also. Sometimes you cannot do anything for some aspects of anything. So you hope it works, and it did. And this is our kind of a stack test rig. Vibration test, shock and vibration, a lot of things. So the oxygen purity remained the same. This is all laboratory tested ceramic. Then, as I said, this is an unlucky one that didn't go to Mars, which means we have to make a lot of the cells show every one will work about the same, so they can pick any based on JPL's test result. So we cannot say only one of these 18 will work. We have to ensure. So we made 21 stacks. By the time we figured out the process of making the cells, sealing, all the process was different. There was a lot of intricate things. It's not magic, but you don't do it the same way as we have been doing, so you have to make a lot of process changes. We did 21 stacks, and it performed the cell. This is the current voltage. So then we sent, I think, 11 stacks for them to pick one. So this is overall 21 stacks, and then, they also said since we are doing minimum 10 cycles, whatever the Mars ambient to 800, 10 times, we have to show margin. So we took 3 times margin what they like. So I think one of the stack was tested for 60 times. I don't know if it's here. And then we were getting 99.6% oxygen purity each cycle. One of the criteria is it's not like on Mars. The first one is high purity. The 10th one is lost a couple of percent. They said even the 10th one should do that. So structural stability, shock and vibration, cryocooling. Some of it is luck, you just do the best you can. Because some of it, there's no extrapolation. If you did this, this will happen. Since we are doing it for this, there's no literature to depend on. Here's, this is the package unit. We worked with JPL to design the heaters and insulation, and we went through a lot of iterations. That's the packaged one, and then the gold kind of outside is to prevent radiation, apparently. They have electronics to control the operation that has to be protected from radiation. So that's what happened. And then it landed, we watched it. This was a nerve-wracking experience. The biggest of which is you land and send a message to JPL. 12 minutes later, they'll receive it. So it could have crashed. We wouldn't know for 12 minutes. So we're all saying, oh, by the time it already landed, we won't know for another 12 minutes. So we waited and landed successfully. And then there are some heartburn also. JPL and MIT wanted to heat it up to make sure the heaters worked before they tested for oxygen. I said, whoa, whoa, whoa. It's 7 millibar pressure. And then you heat a perovskite to 800 C. Is it going to lose oxygen and fall apart? We have no idea. So a lot of argument. JPL had an identical unit, so they heated it up with no current, 7 millibar pressure, cooled it down, reheated, and applied the current, and it worked fine. So that was, in fact, I think I can say that one of the JPL guys said, I'm really worried, but if your anode material works near vacuum at 800, you have a damn good electrode, which apparently we did. So in fact, that was scary. Things could, oxygen loss, you can accommodate some, but beyond certain limit, it'll go to binary oxides. So that worked, and then we did the first oxygen. What is very nice about this project is this ISRU, In-situ Resource Utilization, has been a dream for NASA for decades. Can we make something that is not brought from Earth? So this is the first time in the history of science something was produced on another planet that not using anything brought from Earth. So we made history. In fact, that's one of the things. That's why Joe and I said, if we retire, we can still be proud of our career. Something, I'm sure a lot of people do make things somewhere else, but ours will be the first time something was made. Then we ran that. One of the, I mentioned the eventual unit has to run for a year, maybe longer than a year on Mars. Well, Mars is, 1 year on Mars is 2 years on Earth because of the longer orbit. So when I say year, it's close to 2 years on Earth they'll run. So we have to show, this ran intermittently, so we have to show it'll run day and night, and then all 4 seasons. Because of similar tilt, Mars also has 4 seasons, just each season is twice as long. So we covered all. So it was ran on Earth 8 times, I have another chart, and then 60 times on Mars. So we covered day and night. Part of the curiosity to run day and night is the ambient pressure will be different, daytime and nighttime. And then it'll also vary. This is the Mars air density. It'll also vary from season to season. Can we make the required oxygen at any time and any season? So it did fine. It worked all 16 times on Mars. Then the question is the oxygen purity. They had a way to measure the CO2 that could have leaked into the oxygen side. If CO leaks, it'll burn instantly, so we can only look for CO2 on the oxygen at 800. And it met way beyond the target of 99.6. And in some test, it shows 99.9, maybe it's 100%, we don't know. So they forced, this one of, when say they, it's all collective, we'll have regular meeting to discuss what the next plan is. What if we make the CO2 inlet side at a higher pressure than the oxygen side? Would it leak? And yeah, there is leak. After the leak, it was 98.85 purity. So if we have pressure balanced it, it was near 100% to the extent we can measure. So NASA called it a huge success. So after we did the 16 runs, we said, the stack is still working, we can do more. I said, you didn't run into any problem. There's no more investigation to do. We'll close that. So September of last year, we did the final run, and they said, your mission is done. This again, if you're familiar with that, you would appreciate that the resistance from the first one on Mars, the 16th run, went up 0.1 ohm centimeter square. In fact, I wouldn't predict such a stability on Earth if we ran it 16 times, heating and cooling. So that was another one of the things, we are lucky it worked that way. So where are we going? I mentioned we have to make 200 times. So we did, because we had to make 24 to 32 metric tons of liquid oxygen. It'll run for a little more than a year. So we made the larger one. I have a short stack that is the full size. But we made it much taller, about 65 to, we made all the way up to 70 tons. If we make 65 cell stacks, 8 of those is all you need for the human mission. NASA probably want 15 of those. So we made it. We had 2 projects. NASA kind of changed direction. Each administration will say, we need to go to Mars, and the next one will say, no, we need to go to the moon again. So anyway, the current thinking, they call it moon to Mars plan. So we want to go to the moon first and make rocket propellant on the moon, and then from there go to Mars, because the gravity is 1/6, so you can put higher payload if we launch from the moon. That's the current thinking. So we had 2 projects. On Mars, I talked mostly about oxygen, but rocket needs fuel. So we had a stack like this and a catalytic methanation reactor. So instead of feeding CO2, if we feed CO2 and steam, we can make CO and hydrogen running over a catalyst will make methane. So we made oxygen and methane, so that will be the rocket propellant for. There is water, but getting water to wherever we land is tricky. If you're going to the moon to Mars, we had to make hydrogen and oxygen. Moon has water ice also in the South Pole. NASA hasn't quite figured out how to dig that and bring it to the surface. It's all in the crater, bottom of the crater that never gets sunlight. That's why it stays ice, but we need to bring it to the surface. But we had a project to take water to electrolyze to make hydrogen and oxygen. The tricky part is, again, seal has to be good. This has to be in a chamber that's outside is 7 millibar. This has to be in a chamber that's vacuum because there is no atmosphere. So both worked. We did identify some challenges, no leak in the stack, but where we mounted to the plate, there was some leak. So there are still more work to be done. This is what was in the Mars chamber at JPL, and it produced the target amount of oxygen and methane. Again, as I mentioned, is 7 millibar outside. So the seal, again, becomes very critical. Not to make high purity oxygen, it has to withstand 7 millibar and 1 bar pressure inside. That's, again, people have not done that before. So that kind of wraps up. I could keep talking, but this is where I heard about fuel cell and oxygen being a problem. Here I am talking about our Mars project. So we're hoping we'll continue towards that, and nobody has done that before. That means NASA will trust us to make the larger unit. And will it happen in my lifetime? I hope to live long enough to see manned mission. Last year, Time magazine selected our, I didn't mention, MOXIE is the clever name MIT professor came up with that stands for Mars Oxygen In-situ Resource Utilization Experiment. That's why NASA wanted to call the SOEC SOXY to rhyme with MOXIE. So Time magazine picked MOXIE as one of the best inventions of 2023. So we didn't know they were even considering this, but when it was published, we are pleased to know. We have other projects. So I talked about the solid oxide electrolysis stock. We can make hydrogen, we feed CO2 and steam, can make synthesis gas, can be fed back to make power, or we can take stranded methane that's burnt, goes to waste, run it to make synthesis gas. We can also take the synthesis gas to make aviation fuel. So those, the four corners are the four technologies we primarily focus on. I think that's the end of it. Thank you. And you're all welcome to just set up an appointment to come visit us. We can show you around. And we have a lot of, Raymond recommended a lot of students. They started as interns, and many of them became full-time engineers. And we will be, if our plans work out as we expect, another 6 months we'll be hiring people. Right now we have close to 40 people. We'll have 20 more. Thank you.
Let's take some questions. First question I'd like to ask is, can you give some advice if you were a student right now? I was really impressed with your bicycle picture. I can't imagine.
It became a bicycle rack since nobody lives there. You can leave a bicycle for days and days. It'll still be there. Just people just put their bicycle and you know all about those kind of things.
What would you say to someone? What can they expect in their career? I mean, pretty amazing.
It is amazing. Like I said, and I didn't know the path I would take or what things will lead. But I think just be hopeful because the only thing I would say is don't get scared. The proposing to NASA was scary because they said, oh, it has to make high purity oxygen on Mars. It has to go into launch. It cannot weigh this much. It has to fit in this. I used to joke to Joe, if they're given all the requirements it has to meet, I would say there's no way we could do that. Sometimes things look scary. Unless you dive into it, you don't know if you can do it or not. And especially something nobody has done before, just jump in because you won't get another chance. If we had turned that down, I won't be here, or we won't have a company. We would be looking for jobs. Yeah, just be brave.
Questions you got?
Yeah.
I've got a 2-1 for the full-size unit that would be able to sit on Mars to fill the oxygen and methane,
Yeah.
or just oxygen. What's the power requirements look like for that?
That's about, okay. I'll start with this. This was, the stack itself took 50 watts of power to split the CO2 to make oxygen. But there are heaters and pumps, all those compressors. So the total power is 300 watts. It was powered by a battery. The battery was not charged by solar panels. Early days of rovers, they used solar panels. I also mentioned Mars could have dust storms. So that's the risk. If the solar panels are covered, then the efficiency will go down. So this one, they use what is called radioactive thermoelectric generator. So that only puts out heat, and there's a thermoelectric device that charges it. For the Mars manned mission, they're talking about nuclear device of sorts. They have small modular nuclear device. So I don't think they have decided what it would be, but it'll only take 2 kilowatt power just for the operation of the stack.
And my other question was, when you were first trying to launch your company, what's the process? How do you make decisions as far as when you were assembling your initial team? What was that like?
Okay. We At the peak of this MOXIE project, we had close to 35 people working on it at Ceramatech. A lot of them were borrowed from other teams because they had the scale. Our core group was 15 people, so we made an offer to all 15. They knew us very well. The team has worked, hours in similar project for 30 years at Ceramatech. When Ceramatech announced they are closing down, I said, go till December 2nd, otherwise I won't hit my 30. Not that it makes a difference. December 2nd was my 30 year when they closed down. We made an offer to all 15 people, and 11 accepted, and 3 thought it's too risky because they knew we didn't have any business experience. So 11 came over, and the people who turned down came to us a couple of years later, and then we hired people who used to work with us at Ceramatech 20 years ago. So yeah, that's the start of it. And we were lucky to have some projects. Ceramatech used to get a project every 2 or 3 years from a Japanese customer, and they trusted it's the same team that's starting a company, so they gave the new contract that would have gone to Ceramatech to us. So that got us year 1 started.
Other questions?
Yeah, please.
So obviously there's a lot of different parameters that you have to think about with like being on Mars versus being on Earth. Was that time difference? That's really cool. Do you have to take that into account, the way that time passes differently on Mars?
Yes, that was not our responsibility. Once we delivered, it was JPL's. The Martian day is 24 minutes longer than Earth day. So every day, their schedule is 24 hours, 24 minutes, and the next shift will start after 2. So in fact, it's kind of, NASA has done a lot of studies. Anytime, not this mission, any Mars mission, they reset the clock. The engineers who monitor this will have not 8-hour shift, but 8 hours and some change. So after 3-4 weeks, their shift, instead of starting at 8 a.m., will be 11:30 or something. And they are not mentally stable. People walk and run into things because it's not like night shift, day shift. At least in 2 days, you can adjust. Every day it'll shift by 24 minutes. And yeah, at least for the first 6 months, they aligned their time to Martian time. We didn't have to do it. That was not our role to monitor that. Well, I'll be back in 4 years. Yeah, please.
So it sounds like a lot of this technology was built on work that had been done at Ceramatech.
Correct.
What would you say is the split in terms of technology development between what was done at Ceramatech versus what OxEon took and then pushed into this?
It's a continuation of what we did there. Ceramatech management didn't care what we did with it. In fact, we gave a list of these are the things we are going to do at OxEon. If you have any objection, if you have any concerns, let us know. They never came back. So it's a continuation. Like I said, I was at Ceramatech for 30 years, and OxEon has been around for 6 years. And Joe started in 91, and many other engineers have been 20 years. So it's a continuation of the work we did. And they didn't have any objection. Alex, you should know this.
What aspects do you think are the most important to continue research in regards to? Do you think like the electrode and anode, or what area do you think will allow for solid oxide fuel cells to be propelled into, like full commercialization?
Yeah, the full commercialization requires 2 things. On Mars, it has to run for 1 to 2 years. Even from start to finish, there's 10% degradation in performance. You can build it 10% larger. On Earth, it has to run, they keep shifting the goalpost, as I say. It used to be, it has a run for 5 years, now it's 7 years. Cost is the biggest part. If we cannot make it affordable. They always have hydrogen production cost should be so many dollars per kilogram kind of thing if you don't meet it. So that, I don't want to sidetrack it. We are thinking of building the manufacturing facility to bring the cost down. And the performance degradation, we are still not quite there. We are working on it. And the Mars requirement is different. We have some ongoing project to address something specific to Mars.
Let's
Yeah.
take one last question, then if you've got other questions, then come down and talk with Elango.
So, you said you essentially just stacking these cells, but you can't just put them face to face. So how do you separate that out?
This interconnect plate stays between. Later on you can come and. This has the gas channels on both sides. This separates the cell. So this is also an electrical conductor at high temperature. So it's almost like adding a series of batteries in series connection. So this is the gas flow as well as electrical connection. So it keeps the CO2 and oxygen separated. Does that answer your question? Okay.
Let's give Dr. Elango another.
Sivaraman.